welcome back to the final panel of the Montreal Salon. So Khaled, our Khaled, has kindly agreed to chair the final panels. So Khaled, please.
Thank you, Sherman. I think this particular panel definitely is bound to generate some interesting discussions, because here we're talking about how we can use generative AI in order to design innovative and novel radio architecture design. And there is no question that the use of AI and the large language models, particularly graph neural network, to co-design the physical layer and even the medium access layer. Basically, there has been a lot of interest, and the idea of using generative AI models, such as the diffusion models or maybe the GANs, to automatically design novel radio architectures is receiving a lot of has been receiving a lot of interest recently. For example, they use what they call as radio gen to generate optimize antenna arrays or configuration. Also, they use so this is a very interesting development, and we have 4 questions here that we would like to talk about, and we're going to try to allocate 15 minutes per questions, and hopefully we're going to conclude with a lot of new insights based on this. So the first question is basically we're looking into the potential advantages for using AI and machine learning. How can we leverage that for advanced radio hardware design? And who's going to try first?
So we touched upon this yesterday. Thank you, Chairman Khaled. I think we had a bit of a consensus. When it comes to the physical layer, incredible results have been shared in the literature, and we see constellations that are completely unexpected. However, I have some reservation regarding whether this includes a variety of real-world impairments as one. The other one is dynamics. We talked about it, how the AI/ML optimization can track very rapid propagation channel changes going around a corner at 14 kilometers per hour car, etc. Adaptation and recomputation, it seems challenging, latency and the like. However, this tremendous opportunity, and we touched upon a little earlier, I think we are in the same page with Gerhard in this one. When you get into the layer 2 and 3 with very large MIMO arrays, beamforming combined with resource allocation, scheduling, tracking, etc., narrow beams at the, well, let's not call it millimeter wave, as there is very big issues with coverage, as we discussed, but that's a different topic. But even at the up to 7 gigahertz, which coverage is still not too impaired, except at the cell edge, perhaps, there is still opportunity for significantly larger antenna arrays that it's already a dominant problem, as long as it does not blow up the power consumption budget. But I think the opportunities are great, and mostly in the layer 2 and 3.
Excellent. Gerhard, please.
Yeah, so, I mean, what Ronaldo was alluding to is very much what is later on done by each equipment manufacturer individually that doesn't need to be standardized. I want to touch on standardization in this context now, because, I mean, if we have AI/ML, let's assume we have one big humongous machine sitting there, one model that can generate the transmitter and another model that can generate the receiver, and we're done. Then 3GPP standardization is toast. All we have is this one single model that can be maybe patented or not, and that's the end of the story. So the question, therefore, is that really the future or not? My experience with using advanced AI/ML has been always that we do have a linear system for many different parts. Like, I mean, radio waves linearly add on to each other. So the wireless channel is, in general, a linear system. There are components that have nonlinearities, and there where we do see nonlinearities, like the channel estimator, where we do matrix inversion and these kind of things. Obviously, we've seen with Wolfgang Utschig and the Nokia paper from Stuttgart some very nice results on replacing the MMSE channel estimator with some AIML algorithms. But that means still we take one thing into account. The channel is linear, and we have system knowledge. We build our system understanding and replace components where it makes sense with AIML, and that is then not the end of standardization. That's exactly the opposite. So that's why I just want to point these two extremes so that we don't think that we are going to run along this route, because many of these papers suggest that it's going to be ML everything. And if I think of Wen's keynote, Once Upon a Time, you also sort of said one big AI engine, and that's the receiver. I don't believe in that. Yes, I think still we can use our smarts to be smarter. And the other thing that Reynaldo mentioned is on the receiver implementation side, we always forget that our linear system becomes nonlinear at the A to D converter, because any wacko constellation has to be sliced and diced at the A to D converter. So we forget there are A to D converters, there's phase noise of the down converter and up converter, and there's phase noise all over the place. There's nonlinearities that have to be compensated, all these different parts of the RF impairments and analog circuit impairments that we have to take into account, where I don't say we cannot do it in some kind of a future, but I think the path is far out. So I have strong hopes in AIML, but I still believe our brain is really needed for a correct system modeling, and then putting the right pieces, attacking the right pieces, approaching the right pieces, and replacing with ML.
Please go ahead. Sorry, and then Wen later.
No, let me share some of the work that we've done on that transmitter and receiver architecture using AI ML. We focused on one area on the digital pre-distortion, DPD, and with the multi-carrier OFDM and high-level modulation scheme, and we went to 1K QAM and then 4K QAM and even 8K QAM. And AI helped us, neural network, to, after offline training, and then we use it for online, the trained version, and it enabled us to actually do multi-carrier OFDM with a low PAPR and linear for, and reduce the DPD complexity substantially. It didn't eliminate the DPD, but it reduced it substantially. So this is still ongoing research that we are doing.
Very good, thank you. Wen, please.
Oh, yeah. This is the generative part of AI, but I think we already talked about the physical layer, the digital processing part. Is it an AI completely model replaceable or not? Actually, I was trying to draw at the one in my slide 4 or 5 years ago from John. So I still keep the inner channel model untouched. So that means the decoding, modulation, and all this little. But outside this, there's a big opportunity for AI to play. And then we sort of discussed yesterday and today is the scheduling and whatever resources and beam management that can be done. So that's being given. So with the radio head, how to do the classical at the radio frequency, that design methodology today is a very classical RF engineering process. They have RF tools, and then mostly a plan planar-based printing, planar-based technology. But with the design, we all with a strip line and all this. But with AI, now we start to show some of very strange layout figured out by AI is also good in performance, in the compactness, and all the others. So that's where it's a very attractive direction. And some of the new results, we also discovered that in the very compact antenna, handheld antenna space, we were before not very successful meta antenna, very close spacing, but now the AI figure out some other structure could pack even more radio antenna. So this is the generative AI that beyond the engineering experience of course, every design we have to simulate and test. Eventually, it is if you're lucky, you get a few of them are very good. Some of them are not really satisfactory. But overall, the cycle are very much accelerated, as well as the thinking of the topology and especially when you get to EM level of that computing, this is a very attractive actually. But if it is further connected to the automatic manufacturing or printing process, then the whole radio cycle could be much more optimized in terms of thermal efficiency, energy, power, and other things. This is one thing I think it's a new area.
Excellent. All right. Gerhard, please.
Let me start the second round. Yes. So for me, let's talk about one thing. And I put this conjecture out also last week at an AI summit of Vodafone, saying, dear operators, you are using the wrong argument for arguing for more spectrum. Because it's always capacity, capacity, capacity. And if we look at the data rates over the last couple of years, they've been flat. I truly believe they're going to be exploding with all the new prompting that's going to be happening with video and motion prompting, but that's a different story. But the argument has to be in line of what you were just touching on, meaning energy efficiency. And so instead of going in constellation size, Rahim, which is fun research, to crazy amounts, because I mean, if we double the spectral efficiency by going up in constellation size, we have an exponential increase in power consumption. And not only due to the PA, but also due to the phase noise requirements of the mixers and oscillators and these kind of things. So people always forget that there are other parts that are in the radio chain that also are affected by that. So instead of saying we need more spectrum because we have a capacity crunch, if we were to go out there and show if we have twice as much spectrum for the same data rate, we can halve the power consumption of the current networks. We have a complete different line of argument. We're going to paint ourselves green. It's going to help the operators to spend less OPEX. And people are going to be happily embracing the industry as saying we go green. So that's why I put this out, as I said, last week at the AI Summit of Vodafone. For the first time, I would like to, and that's why, of course, I come to my gearbox stuff again, but I would like to propose thinking differently, not increasing the spectral efficiency, but saying we need more spectrum to go green. And if we think of that, then we come to these crazy things like spiking, impulse radio, whatever. We can go up to 4 bits per second per hertz with that easily, with a SISO channel. Be very energy efficient, not spectrally efficient, but very energy efficient. And then you can add MIMO and stuff like that for that. And that is by nature nonlinear modulation. And then it turns out on the equalizer receiver side, a lot of ML stuff starts kicking in like a fun toolbox. So what I'm trying to put out there as just a line of thought, let's think of leveraging advanced radio hardware design in terms of thinking of good old spiking radios and like ultra-wideband spiking, and think of the potential that we have there, and then use that also in the line of argument for grabbing more spectrum, not the way now has been done so far, where we say, the operators say they don't need more spectrum because the data rate is not there, but if we can say, you double your spectrum, and you have or even quadruple the impact in terms of energy efficiency, I think that's a line of thought. I just want to kick it off.
All right, so I'm gonna, okay, so we have Wen, Rahim, and then maybe I'll ask Ronaldo also, because we had a lunch in Dresden at the summit, and the spike communication came up, and Ronaldo has a lot of thoughts on that, so maybe he would like to say something about it.
Yeah,
And John, okay.
I'm not
So
in
Wen,
that conversation of a spike communication, but so far in my mind, the optimization of the efficiency or energy efficiency for the radio component, well, we will go to many antennas, that's fine. But is that we need to make an entire RAN network as some kind of a quantum burst. So you have your time burst, but looks like a continuous everything. But then in the micro scale, like a millisecond level, your measurement, your reporting, all the control, your payload should be a burst. And most of the other time you can equalize your duty cycle to shut down the whole thing. That's where probably the clean way, if you need to design new standards to reach that. Not necessarily, because when you have equipment going on, you have a radio power transmission, but your base platform, everything, operating systems, and etc., you continuously running all this thing. They still consume energy.
I'll have Rahim first, please.
Yeah, no, thanks. No, I just want to, I agree with what Gerhard said in terms of the energy efficiency, doubling the bandwidth, etc., and keep the data rate low. Obviously, we did this work in EU-funded project, if you remember, Gerhard, called EARTH project, and that was the most of the things started from green radio from there. But when I said you go to high-level modulation scheme, it is effectively you can reduce the power-hungry order of MIMO, because at the end of the day you can have it for the same data rate if you go to high-level modulation scheme, and you can drive your signal close to the nonlinearity of the PA. I think we need to look at that trade-off, how much you can reduce the RF chains for the massive MIMO and etc. versus the modulation level schemes. So it is not only one sort of dimensional look at the things that the spectrum only. Thanks.
So can I,
Please, John, go ahead.
So I was pleased when one of my funders at Stanford is Intel, and they gave a presentation there. One of the directors said, I took your class 25 years ago. Do you remember me? And I didn't, actually. But he said, the only thing I remember from the class was you getting up in front of everybody and saying, if somebody comes to you with a factor of 2 in spectrum or a factor of 2 in power, you always take spectrum. And you can get that right out of Shannon's law because of the logarithm that's in there. But that's for today's designs in 5G. They presume that. In fact, if you look at the multi-user theory in the capacity regions and so forth, and you look at that problem with spectrum sharing, it's not a factor of 2 savings, it's a factor of 10. And my students have been publishing on that recently the last couple of years, and there's interest outside. We have some companies that pursuing that. So I think there's an even better argument, and it's within the same spectrum. But the idea of everybody gets their own dimensions has to yield to spectrum sharing, where users can occupy the same spectrum at the same time. Not the old, 3G spread spectrum stuff. That's got flaws in it. But from an optimal standpoint, you can actually do that type of thing and save a lot more energy. So I would augment the argument, but say you have to really understand the fundamentals. And what happens today in 5G designs, our best designs, is that we kind of presume that the channel has enough degrees of freedom to support all the users in massive MIMO. And that's not really true. Just because you throw more antennas at it does not mean you get a higher ranked channel.
And we still, sorry, John, but just one thing there, in your line of thought, it's still a single link kind of way of thinking. And you're talking exactly about the other way of thinking, which I think is super important.
I agree. It's multi-link. It's really the number of degrees of freedom that you have. How can you best exploit them when you have more users than you have degrees of freedom, basically?
Great. Reynaldo, last word.
Yeah, so let me follow it up. Comp theory has been incredibly powerful. Shannon context and then multi-user detection by more recent researchers give us a direction to follow, which has proven extremely generous and fertile to come up with new radio schemes. However, a word of caution. So we know, for instance, that impulse radio, BPSK, pulse position modulation are incredibly energy efficient, no doubt about that. However, the reality here is one of standards. We have OFDM is the king, and 5G continues with OFDM, and we hear the service providers say, you can have any waveform you want as long as it's OFDM, and my physical layer is a software upgrade from the last one. I think they're going a little too ballistic because of economic climate. They're going to find that 2 or 3 years down the road, through microelectronics improvement, they're going to have to change their physical layer boards because they have to keep up with the improvements and with the competition, whether it's power consumption of compute power or combination of both. And when they do that, I think there is opportunities to changes in waveform. But I think the waveform changes are extremely challenging, and such a radical switch from OFDM to impulse, I'm saying comp theory tells you it's a valid argument. The practicality of putting it through 3GPP, I think, are daunting. That's one. The other one is when you look at beyond the one link, which I totally agree, we need to have a system view, not a link view. And we know cellular systems are interference limited. And you don't even see that if you're doing AWGN comparisons. I can give you a little anecdote, don't want to say any names, but we all know very friendly colleagues pushing really hard for some new waveforms that do particularly well at high speed. And they show all the results at 27 dB SNR. So I said, look, you have to speak the language of the community. Do a full system simulation with 21 sectors, wrap around this many antennas, then tell me baseline OFDM 5G, and then tell me your waveform, how much better do you do? Otherwise, I cannot even translate the charts you're presenting. So here is the same story. We have to do system level, multi-user. It plays a very important role, but my closing remark is also one of caution. In my team, we looked very much at all sort of improving capacity, and I'm always looking for the extreme case that should still obey laws of physics. And it turns out that if you ask a multi-user detection advocate on the uplink capacity, how does it scale with number of simultaneous multi-users? And you get a very fascinating question. It goes up to infinity. And how can that be? Well, the explanation is very simple. Every user is bringing his own power. And so you keep adding more power, and you can keep adding capacity. Well, at some point, your LNA is going to melt. And so let's watch out. And as the overall capacity is growing, the per user rate is actually going down. So yes, comp theory, multi-user detection, we need to go in that direction, but let's proceed with caution. Let's not, melt the LNA.
All All right, please, John, please.
Yeah, I don't want you to misunderstand. There's nothing in anything I said that changes the OFDMA, and it does include very specifically the interference. That's the spectrum sharing part of it. So certainly, if you have a lot of users in a given spectrum, the precisional requirements will increase. So there would be a standards impact there. And then also on how you do the exact beam forming, whether it's all linear or whether you add kind of successive pre-coding or post-coding, uplink, downlink to it, which will increase the precisional requirements. But I think those are within the realm of what could be contemplated as the next few years. So every 18 months you get a new 3GPP standard, or maybe every 3 years on the Wi-Fi. There are ways to address all of that I think could be melded into the evolution of the technology. So, but I agree, going to all new waveforms and all that is probably not worth the effort, but nothing I said implied that was needed.
Excellent, thank you. So as I said, I was expecting, and this is happening, that this is going to be an interesting panel. So I'd like to move to the next one. I think this is also going to be very exciting, because we're always talking about having generative AI, we have an agent to be automatic and all of that, but here we're trying to do kind of a lot of things at the same time. So the question, can generative AI, together with large language models, and at the same time, human-in-the-loop solutions, enable kind of innovations in radio systems? So it's like, this is very interesting, and I'm going to give the floor first to Reynaldo, then I'm going to go to John, and then Gerhard.
So in my natural style, let me throw it out there as a provocative statement. So with all due respect, generative large language models, I call them autocomplete. And if you ask anything of it that it's not in the database, and it could have read the entire internet, but if you are outside of the training set, you're going to get nonsense. So by definition, to me, it's oxymoronic to say, give a prompt that says, give me a novel radio architecture that has never been invented. Well, by definition, you're asking for something that is not in the training set. So autocomplete is going to come up with a token with high probability, whether it's just a token, as in the inference, or whether it's reasoning as it providing you with the several sequences that have high correlation. That's all it is. We call it reasoning. It's going to be nonsense, because by definition, you're asking for something that is not in the trained data set.
Thank you. John?
I wasn't honest, but what I will say is that generative is hard. We all try to use these things to. What I find is it accelerates the way that I find my misunderstandings and all my mistakes, all the things that I really should know, but I'm too embarrassed to admit I don't know. I have to go look on ChatGPT, I go look up that term. And that kind of stuff, it helps a lot. Or what's the flaw in this, or can you summarize something? But once you start to press it, to getting more creative or doing things that are, then it starts to hallucinate. And if you don't really know what you're doing and double check it, it's easy to get confused, in fact, by that. So I'm not sure it's gotten to this point yet where it really is creative, other than in very controlled environments like what you were talking about with the board level design and so forth. It can find better layout or better chip layout, because it can just exhaust all the opportunities out there and find the best design from among that. But when it actually has to be creative, I found that it's only helpful in finding my mistakes, so that I know that mistake quicker, and I know, okay, that's wrong, I should not go that direction, I need to try it another way. I haven't really seen it being more human and actually creating something, and I say, well, that's really new. More it's like, it explains something better to me, and said, that's a really nice explanation that I never would have thought of myself, that it found somewhere on the net, but it didn't really solve any problem yet that I know of that somebody else hasn't already solved. So that's a kind of a limitation. So I wonder on the generative, just how generative it really is yet. Maybe some others have had better experiences, but I haven't had that yet.
Well, let's listen to Gerhard.
Yeah, so I mean, I call it interpolative AI because it can only interpolate between the data set points that exist. Now, if you think of it, a student of mine started an experiment, taking raw IQ samples and trying to find out by analyzing raw IQ samples which equalizer to use. A zero forcer, MMSE, sphere decoder, depending upon SNR level, whatever. All it had was this stupid system, was the raw IQ samples. And it came out with 99-point high precision of choosing the right equalizer for the right situation. So that's pretty impressive. That means, I'm not saying that it's, but that's still interpolation set, you know? It's still within the interpolation set, but it's amazing to see that, because this obviously can give you a big bang for the buck by choosing the right equalizer for this kind of a situation. Now, if you think of Gottfried Ungerberg, who just turned, I looked it up, not with generative AI, 85 years ago, a couple of weeks ago. He is sort of the trellis-coded modulation inventor, if you remember that. That was doing coding and modulation jointly, and we've later on found out we don't really need to do that. But then we found out we do need to do that, because if we do this in a turbo loop, first decode and then first detect, then decode, and go back again in the turbo loop, we can actually improve. So there is, so using the turbo loop means there is something in there if we look at this in some kind of joint fashion. Then we have the channel estimation. We have to do turbo on the channel estimation, the detector. Also, this is called turbo equalization. And then we do a turbo loop on the decoder. So if we just think of the standard bit pipe alone, I'm not talking about synchronization, all these other things, just pure physical layer bit pipe. There's so many intricate things happening there that have some nonlinear correlation, where a nonlinear system as an AI actually could come up with some benefit. I'm not saying that we should just jam AI onto it and out comes a beautiful solution. We should first turn on our brains and look at the problem. So if we look at that, can that have some architectural innovation? That's the question. I truly believe there is the potential, and I don't have the key to it yet, but I truly believe there is the potential because we have these nonlinear correlations between different parts of a seemingly linear modem.
Very good point. However, are we mixing a little bit machine learning, which is an amazing optimization tool, with large language models, which I think they're two different beasts. So my comment about autocomplete and the limitations, and you call it interpolation, I call it what I just said, is on the large language models. Now,
yeah, that's why I started out with the example of my student.
Yeah.
Because if my student, because that's a large language model problem, just using the basic IQ data set and trying to understand which equalizer to do, and then he came up with a 99-point high precision on where to start your turbo loop and which algorithm to use in which kind of the turbo system. So that's where it's machine learning combined with large language models. Yes, that's exactly the combination I'm talking about.
Wonderful. All right. Any other comments? Please, Wei.
Yeah, I can think of the two aspects of the scenario we can consider to using the LLM. From the theory part, I think in the information theory, I think that's quite the classical topic that, especially for the MIMO broadcast channel, so far I think the very limited results have been approved, except the two-user MIMO broadcast channels capacity region. And also recently we see the successful use of the LLM by the terrorist tool to prove some of the theorem or conjecture in the mathematics. Then as a branch of this, the mathematics, the information theory could be pushed further by utilizing the LLM to find some of the theoretical proof of some of the unknown results. I think that is one possibility because of this mathematical proof. Secondly, I think that from a product point of view, that is the wireless testing engineer. Usually, they have to go the on-site and then try to different way to figure out why this coverage is not good enough. And then if we can just introduce this prompt, saying that, okay, the engineer go to one place and then to give some input in mind and to suggest some solution from this LLM and to analyze this data behind of this specific site, for example, the antenna configuration, modulation, users, or the frequency band, or the SNR levels, different parameters, and it give us some of the diagnosis of this problem and suggest some of the further improvement. I think that may be the another improvement for the existing wireless testing.
Please.
Yeah, so just a comment. I guess that for this generative AI or with even a large language model, this is offline. It's not the runtime that the real equipment running that. It's the methodology or our research efficiency or R&D efficiency. Depends on whatever you want to do because they can generate. Then John was commented it was just proof things run with that part of a saving efficiency, and this is the first time I heard that somebody can prompt the large language model come out the equalizer. That's another, and with 90% correct, or that's amazing.
Thank you. Ping, please.
Yeah, I'm more of question like because many years ago, people talking about the, when we designed the MIMO system, we have an antenna guy keep tuning the antenna so that to the point that they optimize the antenna design. Then the algorithm guy will given the antenna, then I do the tuning my algorithm so that can have optimized algorithm. Then there were some proposal to do the joint design, but it never happened. Because I think we don't have tool to do it. Like everyone has their own tool. Then when you put them together, seems too complicated become problem. But I'm just wondering, this large language model, essentially you just feed them both knowledge. They kind of generate something with the combination of knowledge. I think that could potentially have some new things coming out. But I don't know. I mean, like seems it's more reasonable in the sense of this kind of problem we used to divide them into components. This guy may come out to some joint solution. Yeah, I don't know.
Well, I think it comes back to Wen's point about verification earlier when you start to do that. Because what I've tried the information theory thing where we have an unsolved problem, you give it to Chat, and it hallucinates badly, and you have to test. You have to know enough yourself to be able to apply a test to it to say, simple example. And this part about all the complicated systems and so forth, you have to verify, and you have to have something that's able to sit there and let's try some simple system examples and see if what this output just gave me is actually a solution, or was it just trying to please me by answering my question? Yeah, great, yeah, oh, wonderful idea, and here's how you do it, and it spits out something that's not correct when it gets to the end of that. So that's where the generative part, I think, it may happen in the next 10 years, but it's still, not to the point where it's really creating. It's interpolating, as he said, because it's got this existing body of things that it's looked at, and if it's not in that body, then it's going to be hard to find. So sometimes if you ask it for a proof, if there's a good proof out there already somewhere that you didn't know about, it's probably going to find it and say, okay, here's a simple explanation. And you say, you look at that and say, wow, that's a whole lot simpler than I thought it would be. But when you try to give it, and I've tried it a few times, And even a few times where I've asked it to use something that's supposedly proved and known, and it will come back and say it's wrong or something like that, but I haven't seen it yet being able to create something that wasn't there yet. I hope that happens because it'd be a great augmentation to our abilities, but the verification is really important when you start pressing the edges of what's known. The existing large language models start hallucinating far more frequently than they do with easy questions. So,
Bean, and then
I just
Rinaldo.
want to add. I guess I don't think we think that we can take the vanilla large language model to solve our problems. We're going to assuming you're going to make more. Based on that model, maybe derive your own specialized model in the sense that's why today people are all talking about the going toward the agent direction, because the agent allow you to reduce the large problem space into the small, more expertise level type of space, and with the capability to leverage your existing tool and all memory and so on. So I think that direction is more suitable for us, because there's nothing to say why we don't focus on the data into our design space. I can get rid of lots of data I don't need it, which actually that's a part that causes hallucination. So I see this direction. At least the AI is moving toward direction to remove all the problem, not all the problem, remove any problem we think it with associated with the large language model.
Yeah, Gerhard, using the word interpolation just brought to my mind a recollection of a project we had. This was a junior intern, and we were trying to do ML in propagation prediction. And we thought this is an example where we have a lot of data, we thought. When you compare to the number of parameters in your model, then it wasn't that large. But nonetheless, we were in learning several years ago. And then I thought it's really complex world out there. It seems to be ideal for this type of tool, because we cannot just do electromagnetic theory on it. So that was the challenge. And then the student came back. Of course, we told them you have to separate the data into training and testing, because we want to do RMS error of the fit versus RMS error of the prediction once you have your model. And so a student came back so happy, and the error was incredibly small. And then I said, okay, very good. Now show me exactly in the physical world, I'm kind of a practical down-to-earth engineer guy, where are your data set training points and where are your data set prediction points? Well, it had chosen every other point. So this is your training set. This is your prediction set. The interpolation was fantastic. Then I said, no. You use this route that the channel sounder took to do your training, and then try to predict over this other route. Miserable failure. So validation, I think we're still in the very early stages of learning how to use this. Now, don't get me wrong, extremely powerful tools, but we're still in the learning stages of how to best put them to good use.
I don't know if anybody else has this experience, but we have good students at Stanford. I'm not impairing. You don't know how many times I have had to go through this exercise where they used the result to train. So of course they got a really beautiful result that they're very proud of, but you have to say, well, no, that's against the rules. You can't train with the thing you're trying to estimate. You have to get it somewhere else. The whole area of channel prediction, there are probably hundreds of papers in conferences, IEEE, where the students are making that mistake. And you have to be very knowledgeable about the area to go in like you did and say, wait a minute, where did you get that training data or that ground truth or whatever you're doing? Often that mistake is being made. And part of it is, as educators, we have to make sure that it just doesn't go wild on the AI without realizing what it is you're trying to do, because the training is very, very important.
Quick follow-up. There is a tremendous amount of activity in the academic world and in publications. Making measurements, designing your instrumentation, collecting the data is painful. It takes time, and not everybody has the resources or the time. And so now it's become very popular to do ray tracing and call it your ground truth. Whether you call it digital twin or you are just simply honest to truth and call it ray tracer, it's the ground truth. And then you do prediction and you get amazing results. Yes, but you forgot that you made an incredibly rude simplification of the infinite complexity of the real world. And I'll be the first one to tell you, ray tracing in particular at the higher frequencies, and I've written my own ray tracers, are very bad. In line of sight, they are optimistic because you don't have the little tree, the shrubbery, the stop sign. And with a 1 degree or sub-degree beam width, all of those objects are measured. And then you think it's free space, it's not free space. Then you try to go around the corner, and now ray tracing fails again because it doesn't find any in your data set, no matter what you call it, which is really, as I said yesterday, it's not a digital twin, it's just a digital cousin, and maybe a distant cousin. And so around the corner, it thinks that there's nothing there because diffraction dies very, very quickly. Well, my very good colleague, Dmitry Shishik, was looking at the data. We measured the data. It was getting around the corner somehow at these higher frequencies. And he observed that, this is why being in the physical world makes an incredible difference, that the AI was going to take a long time to get there. Being in the physical world where we're collecting the data, he observed that there are stop signs at each corner of the intersection. And it has a octagonal cross-section column. So he just put octagonal cross-section metal pillars, did his electromagnetic theory, and boom, the signal is coming around the corner. So now we improved the prediction of ray tracer, but only after you added some more realism of the physical world. So call it what you want, but doing papers based on ray tracing as a gold truth, I think is also coming short on the validation, whether it's the wrong data set or it's the wrong physical world description.
Art has, but I guess
I just wanted to, I love the word digital cousin. That's what I wanted to say.
Copyrighted.
Copyrighted, and it indicates that the human in the loop can actually make a big difference.
Big difference. Yes.
Thank you. So on that note, now we addressed number 1 and 2, and we still have to address number 3 and 4 in the next 8 minutes. So if the chair would allow us, we can go for an extra 5 minutes, right? Until 12.
Oh, plenty of time.
Oh, we have plenty of time. All right. It doesn't matter. Let's do it until we stop. All right. So the next question is it's going to be very interesting because it's asking a lot of philosophical questions, and they are probably quite general, so we can go anywhere with that. Because here we're talking about the ambition levels of AI and machine learning. And we're defining somehow 3 levels. Level 1, which is the design automation. Level 2, the design exploration. And it seems like level 3 is the ultimate, is the innovation. So these represent increasing capabilities in the radio hardware design. And the question, can we consider levels 1 and 2 already done in specific domains of the radio hardware development? And then we will discuss number 4 later on, which is more related to level 3. Who wants to take? Thank you, sir.
I just take design exploration. Yes. So honestly, what I do these days, in wireless, not everything, but a lot is about link budget. It's seldom taught in courses, but link budget is more or less everything. And so, but I love it because I don't have to do these calculations myself anymore. I just say the aperture of the antenna, I give it the carrier frequency, whatever all, and it comes up with that. I check the equations, I see is it correct or not. So for design exploration, for things I do, it works beautifully. So that's why for design automation, I don't know about that. For design innovation, no. Because it's just an interpolative system these days. That would be my way of looking at it. So I see level 1, design automation. I mean, on chip design side, I can tell you Synopsys and Cadence have a lot of AI/ML built into their new systems. So yes, that is happening. Design exploration as a wireless engineer, it's a beautiful tool.
Thank you. Reynaldo, please.
I think you just said it in your last few sentences, but I have to assume, without being an expert on it, but I have to assume that it's a ready-made marriage in heaven where you'll have a very high level, maybe even block diagram, and you use the tool to generate C code or Python or whatever it is. And then you say, well, okay, that you need to do validation still, just in case. It's regurgitating some other design, some other code from another project. But if, if it does regression testing okay, then you can go into the really difficult part where very few engineers excel at this black magic of RTL. You're now trying to move into real time, and then you go to place and route. All of these steps in the design of VLSI are very intense in tool usage, which in the past used to be very custom tools by various vendors, as already mentioned by Gerhard. But I think the problem is constrained good enough that seems really fertile ground for, and maybe this already being used in this space, maybe all the way to optimize of place and route in silicon and mask generation.
Okay. Wait, please.
Yeah, I would like to talk about our group recently works on the race configuration by using the deep reinforcement learning without any pilot requirement. So that is totally different from the traditional method. For example, considering that it's a large the array of the race antenna elements, probably the hundreds of thousands, then that's a traditional method to estimate the channel, that it costs the huge amount of the training. So then we try to avoid using any pilot. They say, can we just use the feedback of the end-to-end performance, for example, the error rate or the capacity increase or decrease, and then send back to this black box to configure this the phase configuration of each element of the race. So, and also to verify this is a performance improvement or not, so we also use the traditional method to assume that, okay, we know every channel information perfectly, we just do the optimization and find the best way. And then we find, okay, finally the performance converge. That is verified. This is the deep learning method can outperform the traditional method by avoiding use any the pilot. So I think that can match the level 2 design exploration. But for the design innovation, that is still come back to the race problem, where we can place the race and how we can design the protocol between the base station race and the user to make it more efficient or with less and the overhead. So this is unknown, not clear to us.
Thank you. Please, Wen.
Yeah, so I just try to bring the discussion on a different perspective. If we still expect an AI model have a one-shot correct answer, that is not what we sort of have that conclusion. But even in the interpolation level, because after all, it's still a statistical machine, so they will give you approximately extrapolated, but every time they may, because the nonlinear dynamics will give you unique answer. So that's come out of this machine. For what I see it's going is for a verifiable result in that kind of structure, because generative AI is more efficient than human, whatever other tool design, so they can generate more. So we have more candidates. One way is to use like a Monte Carlo tree search to find which one is probably the better or close to better solution, or you use like a reinforced learning, that more computational effective way to evolve to a solution. And more recent, I think the most successful one is the Google Alpha Evolve. That's a research tool that uses generic selection method. So after they have so many candidates solutions, so they can verify, because assume the computing to verify is cheaper now. So in that way, they can figure out with a verifiable frame, you can still keep optimize the solution that may surpass the ordinary engineer capability to do a better design. Somehow, but this is not really clear reason, because the harmonization of the model, so they can generate certain steps that we not follow our thinking of the rule. So it's like a goal, the goal that beat the human being as number 37 step, that is very unusual. So these are actually the harmonization, but it is within the bounds of a verification. If without the constraint, then innovation is, I have very doubt it will come up, make sense solution. It will be probably garbage.
Thank you. All right, so maybe I will like to move to the next question, because it's very, very well connected. This is with respect to the level 3, I guess, the design innovation. And the question is, what advancement in AI and emergence paradigms are necessary to reach this level, what they refer to as ambition level, in future base station radio hardware design? So this is very specific, talking about the future of base station radio hardware design. Please, wait.
I'm not sure the radio hardware yet, but in the software and somewhere in the mass proof, there are several. Apparently, it's a different paradigm. It's not a chat box style. It is a different, more or less in the agent setup. So they have their own a little bit tools and verifiers and generations, and that seems to progress very well in the software coding domain.
Yeah, so design innovation, I would put a big question mark, but there's a step towards design innovation, which is exactly what I, as a professor, and all my colleagues as professors have to do every day, is we don't hand a solution to our PhD students, we pose a question. And we can smell out questions that make sense. So just as I was mentioning earlier, the coupling of these three seemingly linear systems, I mean, they're not in their coupling, it's a nonlinear problem. So it turns out, I truly believe that the next step would be for us, in terms of not design automation, design exploration, is to be able to start posing questions, finding places where it could actually start posing questions. This is not hallucinating, this is not extrapolating beyond its boundaries, but just using the data set and having a fresh view on that kind of data set. So I'm not an AI/ML large language model architect. I'm a user only and chip designer and of them. So we design ML processors, but still, what I want to say is I truly can think that if the AI algorithm community were to start looking in this direction, that would be then really helping us in terms of design innovation without innovating itself. You know what I mean? Yeah. It's sort of guiding our thought process as we do. I always say during COVID, it was very difficult coming up with new patents because we're not standing in front of the whiteboard, grabbing the pen out of each other's hand and interacting physically in 3D directly with each other, but we just had this 2D screen. So we need this interaction, this asking questions, whatever. But if these systems start getting into that kind of stage, I truly think there's huge potential.
Perfect. Rinaldo, please.
Yes, as we start getting closer to wrap up, let me make some comments. I think when the problem is highly constrained, like for instance, you have legacy language, legacy code, I think it's ideal to say, translate into Python or even give me more application or hardware specific implementation. Fantastic. As we move to design innovation and put the emphasis on innovation, I think we try not to be refractory, but inspirational. I think we need to think really, really hard. What would it take for the current state of AI/ML to become creative? Humans, we have this amazing capability that almost out of nowhere. And I have a couple of examples. I know one example where we were trying to solve the power allocation, MIMO, multi-cell. Oh, it's impossible. And then this colleague of mine came up with the uplink downlink duality. So I took at the problem and I said, well, the equations are like this, but if I wrap it around and base stations become UEs becomes base station becomes UEs, and we know that the solution for that problem with these power constraints, I can map to this other problem. Wow, when would AI come up with something like that? It's not in the books, it's not in the prior, it cannot be subject to interpolation, extrapolation, or even hallucination. It's just not going to happen. So what would it take, my esteemed panel colleagues, to do the jump? And I think there is a lot of talk about human level intelligence just being around the corner. I think this creative process that we are gifted with is very distant to be achieved by machine, my 2 cents. But a fertile area for exploration, for sure.
Any last-minute comments? Wait.
I'm thinking of the topic is for one example, like the Wi-Fi sensing. That has been there for a long time. And if we also recently we have seen the successful use of the creation of music or the drawing by using the large language model or different to the AI models. So would it be possible that I see very few results by using this LM for the creation of the radio frequency or visualization of the radio frequency signals. If we could possibly train the model or feed the data because we have a lot of the data set for the Wi-Fi, and we could feed this data to the model and then to visualize the RF signal for a particular area, and then based on that visualization of the signal, then we could redesign the localization or sensing method. I think that also the possibility.
Okay. Any questions from the audience, please, on anything we have designed? Yes, please.
Relating to question number 2, so like Dr. Wen Tong mentioned, it's offline, and with large language model, we look at that generative AI cross-domain. So at architectural level, we're leveraging expertise from various domains. And we're not expecting the AI to give us innovation in one shot, like Dr. Tong said. So mainly just suggesting, facilitating ideas, and then the human in the loop is actually the expert that will validate the approach.
Very good point. Very good point. Any other questions, comments from the audience, please? If not, then I'm going to pass the baton to Sherman.
Yeah, thank you very much, Colette, for chairing the last panel. So since we have the group photo already, so we won't take any more photos, okay? So to conclude this Montreal Salon, I would like to thank everyone again for your participation and also for your insight and valuable contributions to the workshop. I truly believe our ComSom member will also benefit a lot from the discussion of these workshops. So finally, I wish all of you having a wonderful time in Montreal.
Can we have a last round of ideas to capture for possible next round?
Sure.
From everybody, if you want.
Okay. Yeah. So, John.
Go first on this. There's lots been said about AI, and so trying to get to next levels of everything. Take away the A, and we just have intelligence, not necessarily artificial. And it says in many of the good religious books that God made man in his own image, and we are those intelligent systems, imperfect as we are. But if AI can help us get a little bit better and a little bit closer to that perfect system created, then great, and hopefully that'll help communications as well.
All right, I think I just want to follow up on that. I think that's a very interesting observation. But surely, I think when it comes down to 6G, to me, the key what's going to differentiate 6G from 5G is this connected intelligence. And I think AI, whether we delete the A or I think still intelligence is the key. And I truly believe it's going to be the key differentiator, which is going to differentiate between 5G and 6G, is this integration of AI and communication. And we've looked at multiple topics here. We started with the integration of sensing communication at the beginning, which I believe is going to play a very important role. We discussed other topics such as edge AI, whether it's going to be good or bad, I don't know, but I think I believe it's going to be important. And I think this topic is very interesting. And the comment made by one of our attendees, I think, trying to get the human being inside kind of in the loop, I think that can perhaps play some important role to move us forward.
I think we can focus our intellectual capabilities to think in this fantastic achievement of the last few decades, which is mobile networks worldwide, used by so many billions of people, change quality of life, business practices, etc. I think it's at the beginning. I think we're at the dawn of a new era. And if you think of the immediate opportunities, if you, for once, think beyond the current exciting topic, and you all know what I'm talking about, but think of the interaction, intersection, or triangle of cyberspace, compute, and the communications network. I think that triad offers a fertile ground for incredibly fantastic new applications. I don't want to do business case. I'm not that kind of a person, but you can imagine the value add. Imagine the person who's been paralyzed for neck down for life, and then all of a sudden an exoskeleton with the comms to the network and the cloud to give additional capabilities in terms of dynamic balancing and whatnot, as well as interfaces in the body network, and this person now can walk or see or hear. It's fantastic potential, and that's just one case. But so let's think beyond the AI/ML current focus, and let's focus perhaps in value add to the network with the addition of compute and cyber.
I'd like to focus on applications because they're the driver that makes an infrastructure worth having or not. But in terms of, we touched on many applications, but one type that we didn't is what I call complex infrastructures. By that I mean smart cities, transportation networks, and so forth. And I think in the context of AI, ML, but in particular data-driven decision-making systems, that there's a lot of impact, that everything we talked about in the past couple of days can be brought to bear in terms of these infrastructures.
I think for many years we have been talking about the smart intelligence, automation, namely any words like we have been talking about this. That's always on our wish list. But I think now actually I do see there's a potentially we will have a good tool actually allow us to do that maybe in the next generation. So I think what we really should do is open mind a bit, so we don't rush into something, get a new generation's small improvement, but rather think about, in this new technology, what brings some new potential, larger values. So I think that's a very good area. We probably were at some close point. We may be big, maybe not, but yeah.
Yeah. So I just have some comment on 6G RAN. So I guess we kind of agree that the integration of communication sensing and AI into the 6G RAN represent a major leap toward a more intelligent, perceptive, and responsive wireless infrastructure. So it makes a major shift from traditional data center models to a more holistic, service-aware approach, unlocking unprecedented opportunities in areas such as autonomous systems, smart city, healthcare, and the metaverse, etc. Thank you.
I do think AI is going through a revolution and is going to be dominant in the next decade. So this will be the same thing that we experienced when the internet showed up. So that means that the communication community has to reintegrate it with the AI, to not only use AI as a tool, but have to figure out how to become relevant or at least a part of this next AI revolution. Because otherwise we were going to miss the boat and become irrelevant.
It is one of the problems when you come towards the end, because everybody else has said all the ideas. So then you think hard. You say, what can I do? Say that which adds to everything has been said. I agree with everything has been said. There are so many questions, so many things. Even the ones that you pose and we try to answer, we still not need to carry on and discussing and debating to find some answers. And I think that comes from doing our research we are doing, and then share our experience and what we learned among ourselves as well as the community. But if you want me to specifically say what topics is important, I think we do not talk enough about sensing beyond localization. What does sensing can do, and how the sensing can help AI. I think this is an area that I'm interested to explore more. Another area that I believe that is very important because of the AI computation and most of the processing and computing, I wonder, should we go back to analog communication? So this is a question, analog at the wave as well as analog processing. So this is something that I think that we should go back to basics sometimes and see what we can do.
So I agree, AI integrated with communication is a direction, but I'd like to mention some controversial things in the history of communication histories. Whatever human designed and they put a high hope or high expectation for communications, most of them are failing. If we look into the history of communications, all these very highly focused and the high expectations are all failures. We can talk about more during the lunchtime. So this AI for communications is a very good research topic, areas, and they have a lot of different scenarios to do. It's good for researchers. But for something particularly for commercialization, to make a big wave, we don't know. And usually the most highly hot topic may not be chosen by nature. That is the history told us in communication histories. Thanks.
Great. I would like to bring a topic to the table I think that really needs to be discussed that hasn't been touched at all. That's why I suggested this round, because we haven't talked about the power of AI/ML for standardization. And I mean for standardization, meaning looking at 27 binders and making consistency check. Today, we don't even know if the variable on page 17 is the same as on 2417. Honestly, if we look at the way 3GPP works, it's Stone Age. So the power of using that to make sure that the standard is even consistent and we don't have to spend billions in the network later on debugging these systems, but actually coming up with these systems at a much better validation. Number two is trustworthiness. I see it as a huge potential to build trustworthy systems. Meaning once I have taken a standard and converted it into an interpretable model, I can then do module by module, checking against a Rust or whatever kind of implementation I'm doing, and do formal verification, which I need AI for the modern formal verification methods do that, to really make sure, is that 6G base station a 6G base station or it is an eavesdropper for some foreign entity. So really making sure that we have this kind of level of trustworthiness in many different ways so that we know it is consistent, it is 5G, we can trust it, or 6G, and we can trust these systems. And then, only then, can we think of these beautiful new applications of having our robots being driven by a network. Because if we don't know if the system can be trusted or not, as I can tell you, I mean, we did this study for the German cyber agency, and we found out we could hack into any single component of a 5G network. Didn't have to be ORAN, also that's typical 5G network. There were only very simple cases where if you turned on everything and you were a terminal, you couldn't get in. But from the network side, it was easy peasy. So that's why, for me, the idea is we really have to start understanding how to build these systems in a zero trust kind of environment from design point of view, how to standardize them, to make them consistent. And this is a topic I would really like to explore on, because that's going to empower all these beautiful applications that then are going to drive the revenue we were talking about. Thanks.
Okay, I think the AI, in terms of the key technology, the key thing, I think that data. So far, we have seen that many the providing and exciting research results in terms of the AI-based communication. However, we are lack of the standardized the data set, and also it's not easy to verify or reproduce the results for some of the published paper. Not like the computer science community, they have the standard image or video data set, but for us, we are lack of the standard set. We know that for the big companies like the Huawei, they have, I know one of the data set called the Sensiverse for the integrated sensing communication. For the US-based company, they also developed the RF data set, but it's still not the widely recognized. At least we have few paper based on that data set. I think what can we do next? From the perspective of the ComSci, I think that we can promote this the use of the exploration of use of this data set and promote and recommend to the the authors or the researchers to verify their results by using the standardized data set, so that result could be widely recognized and adopted. I think that is my recommendation. Thanks.
Yeah, thank you for all the panelists for the final words. That concludes our Montreal Salon. So I just wish everyone have a wonderful time in Montreal. Thank you.
Thank you.
Thank you, Sherman. Big hand.